So welcome to today's session. So in today's session, we'll discuss the topic. This is like a continuation of the last topic what we discussed. So quadratic forms, and how to represent quadratic forms in terms of matrices. And next is to find the nature of the quadratic form. What we do is we'll convert the quadratic form into canonical form. So based on the canonical form, we can understand. So we can understand the nature of the quadratic form. We'll discuss the topic. So these are the topics which we are going to discuss in today's class. Okay, yeah, we'll continue. So the first part, what we do is we'll go through various definitions related. So first one is, first initially what we do is we'll discuss linear form, bilinear form, then quadratic form. So this is actually what we discuss, right? This is the topic for today's discussion, that is quadratic form. So then to understand the quadratic form, we'll see the linear form, bilinear form, then quadratic form. So then we'll see how to convert quadratic form into canonical form. Okay. So this is a very important, this is a quadratic form, and based on quadratic form, so trying to understand the nature of the quadratic form is having many applications. This is very important topic. So linear form is, this is a regular thing what we use. Suppose, so we had variables x1, x2, x3, so on, xn, n variables, and correspondingly n constants a1, a2, a3, so on, an. If we write their combination, linear combination, right? Generally we this is what we discuss, right? a1 x1 plus a2 x2 plus so on an xn, right? So which we can represent as shown here, summation I equal to 1 to n ai xi, right? So when I equal to 1, then we'll get a1 x1, when I equal to 2, we'll get a2 x2, and so on, right? So this is what we call as a linear form, right? So this here linear form with one variable, that is x1, x2, x3, and so on, xn. Okay. So if it is a linear, if it is in linear form, how to write or how to represent this in terms of a matrix, right? So this we can write this linear form can be represented in terms of matrices as, so the row matrix a1, a2, so on, an into the column matrix x1, x2, so on, xn. So generally this, if we remember the earlier discussions, A is a matrix where a1, a2, a3, and so on, an. This is X. And X is a matrix which consisting of x1, x2, so on, xn. So when we represent this form in terms of matrices, so we take the transpose of the, this is actually some typo. This has to be a matrix, is always denoted by a capital letter. So this is A transpose into X. Right? This is the linear. So next is bilinear form. So the same kind of discussion, only thing is instead of one set of x1 variables, so x1, x2, x3, so on, xn, here we'll take another set of variables also, y1, y2, y3, and so on, yn. And in the same fashion, if we take constants aij's, right? So where the expression of the form a11 x1 y1, a12 x1 y2, and so on, which can be written as summation I equal to 1 to m, j equal to 1 to n, aij xi yj. So here suppose if we take I equal to 1, j equal to 1, then we'll get 1 x1 by 1, right? So similarly I equal to 1, j equal to 2, we'll get a12 x1 by 2, and so on. So this is called as a bilinear form. Right? So now again, how to represent this in terms of a matrix? So this can be represented in matrix form as X transpose A into the other matrix Y. So here X consisting of the matrix, that is actually here it is a vector R, it is a column matrix. X is a column matrix consisting of all variables x1, x2, so on up to xn. Similarly, Y is a column matrix consisting of all the Y variables y1, y2, y3 and so on, yn. And A is a matrix consisting of the coefficients Aij's. So this is bilinear form. So next is quadratic form. So which is the actual topic of the discussion. So what is this quadratic form? So any homogeneous polynomial of degree 2, right? Any homogeneous polynomial of degree 2 is called as a quadratic form, right? Okay. So polynomial we know, right? So it has to be a polynomial homogeneous with degree 2, right? So if you see here now, so here the degree of this term is 2, right? So here the degree of this term is x1 x power 1 y power 1, so degree of this term is 2. So 3yx, degree of this term is 2, so degree of this term is 2, right? That means each term in the polynomial is having same degree, that is second degree, right? So all are having the same powers, then it is called as homogeneous, right? So first what we can say is this is a homogeneous polynomial where every term is having same powers. Here I am not saying individual powers, right? It is not x power, what is x power y power. So what is that total power of the term, right? 2. Similarly total power of this term, right? The term, third term, fourth term, like this. So all are having same power, therefore we call this as a homogeneous polynomial. Next comes what is the degree of this polynomial, right? So it is 2, right? Therefore it is called as a quadratic form, right? So a homogeneous polynomial of second degree, so called as a quadratic form. Now next question comes, because this what we have been discussing is matrices, right? So how to represent this in matrix form, right? So like we have seen the two types of forms, right? Linear form, bilinear form, same way here, right? So here the matrix, here it consisting of two variables, right? X and y, right? So x and y, so a vector or one column matrix consisting of variables. So here same way x transpose Ax. So how to have this matrix A? Right. So then very simple here. If you see this, this is for our understanding, we can take this as x, this as y, and similarly this as x, similarly this as y. Now if we can understand, like this is x squared term, right? This is y squared term, right? And this is xy term, right? And this is yx term, right? So now 2x square, so therefore 2x square 5y square, and xy term what we had is 8xy, right? Total it is 8xy, right? So now we have to divide this into half, that is 4 here, 4 here. So this term is 4xy, this term is 4yx, both are the same. So 4yx plus 4xy, it is nothing but 8xy, right? So we can verify this. So we know how to we can multiply these two matrices, right? And multiply with this matrix, we will get this 2x square plus 5xy plus 3xy plus 6y square, right? So like this we have to convert the given quadratic form into a matrix form. And if you see here, while doing while having the matrix A, what we have done is we divided this 8xy into half here, 4xy here, 4xy here, right? So that means when we do like this, then it is nothing but a symmetric matrix, right? So that is the one observation or conclusion is, when we write quadratic form in matrix form, matrix whatever we get, this is always a symmetric matrix, right? Symmetric matrix, we know, right? A transpose equal to A, then it is called as a symmetric matrix, right? So that is here. So now, so one more definition kind of stuff. So matrix congruencies. So here congruent matrices. So let us consider two matrices, square matrices of same degree, right? So here, as mentioned, let A and B are two square matrices of order n. When we can say the matrix A is congruent to A, right? So the matrix B is said to be a congruent to A if there exists a non-singular matrix P such that P transpose AP equal to P. Right? Okay. So whenever there is a non-singular matrix P where P transpose AP becomes B, then so B is called as a congruent matrix to the matrix A. So B equal to P transpose AP is the condition required to say that two matrices are congruent. Okay. Now, so with this, the definition of congruence of matrices, the same definition we can take in terms of quadratic forms. Right? So here let us consider two quadratic forms. Right? So already we discussed or we have seen one type of quadratic form, right? So something like, sorry, something like x transpose x, right? This is what we have seen, right? Suppose consider another quadratic form, y transpose by, right? Some other, just like the previous one, maybe it is something like, suppose if I take this as some 2x1 square plus 3x1 x2 plus 4y1 square, like that, right? So similarly in terms of y or some other quadratic form, y1 square plus 2y1 y2 plus 3y2 y1 plus 4y2 square, like this, two quadratic forms, right? So then we wrote them, we converted them in terms of matrices, that then we are getting this x transpose Ax, y transpose A. Now when we can say these two matrices are congruent, right? So very simple, right? As mentioned here, see if the corresponding matrices are congruent, that is B and A are congruent, that is B is congruent to A, right? When B is congruent to A, then we say the quadratic form y transpose by is congruent to x transpose Ax. Right? I think it's clear, right? So whenever the corresponding matrices are congruent, in turn the quadratic forms are also congruent to each other. Right? So that is the definition. So next definition is rank of a quadratic form. I think based on the just discussion whatever we had, I think this immediately we can connect with the definition of this rank of a quadratic form, right? So this, suppose x transpose Ax is a quadratic form, right? So here A is the coefficient matrix, right? Very simple, whatever the rank of the matrix A, right, then that itself is called as the rank of the quadratic form. Suppose this matrix is having rank of 2. Suppose we know how to find the rank of a matrix. If this A is having rank 2, then we say the rank of the given corresponding quadratic form is also 2. So that is the definition. Okay. Right. So next, this is what we are looking for. Actually, this is the base, the important stuff in the entire discussion. Right? So canonical form or normal form, or this some people calls this as the sum of squares form. Right? Canonical form or normal form or sum of squares form. So what is this sum of squares form and how to have this form? Consider a quadratic form x transpose Ax, right, as discussed, and assume the rank is equal to R. Right? Suppose if there exists a transformation x equal to Py. So what does it mean? Some transformation like x1 equal to as was seen in terms of homogeneous, non-homogeneous equations earlier. Something like if we had a set of equations like x1 equal to 2y1 plus 3y2, x2 equal to 4y1 plus 3y2 like this, then we can wrote them as x equal to py. That means so this matrix P transforming x into y, right? That's why this is called as one transformation. X equal to py is a linear transformation, that too. Right? So where here P is a non-singular transformation. Suppose if we take this transformation with this, then what happens is, so x dash, that dash means if transpose here, x transpose x equal to py. If you replace a, x replaced by py. Now we know AB whole transpose equal to B transpose A transpose, right? So now, so this becomes Y transpose P transpose A py. Now if you see this P transpose, suppose if we take this as some matrix B, right? P transpose AP is some matrix because it is a matrix. So then, so we are converting x transpose x into some other y transpose by, right? Suppose if this B is a diagonal matrix, then what happens? Okay. Diagonal matrix means we know, right? So diagonal matrix means only will have the diagonal elements, rest of the elements are zeros, right? So then what happens? So for this we can go back to the previous example. Suppose if you see here, this example, if you see, suppose this 4 equal to 0, 4 equal to 0, then what happens? Only we will get diagonals. Diagonals means it is here 2x square, 6y square, right? Same fashion, sorry, the same way we can understand here. So if this B is a diagonal matrix, then what happens? So Y is nothing but some column matrix or column vector consisting of y1, y2, y3, so on, y transpose. Then B is only diagonal matrix, then we'll get the terms consisting of only squares of the variables like y1 square, y2 square, and so on, right? So whatever, suppose here if B is a diagonal matrix, suppose here 2 is there, 4 is there, minus 1 is there, suppose, right? Then it is 2y1 square plus 4y2 square minus y3 square, right? So that means here what we are doing, we are converting this x transpose x, which is a quadratic form, into another form which consisting of only the some square terms, right? So how we are doing? So we are doing this with the help of a transformation x equal to py. See here p is plays the crucial role. Right? So this is the matrix of transformation, or we can call this as a non-singular transformation, like this. Okay. So how to apply this idea when we take a problem? We'll see it. After some time, we'll take a problem and see how to convert. So this idea helps us to classify quadratic forms into various types. Some more definitions. Now, continuation of the discussion. Assume or consider x dash ax, which is the given quadratic form, where rank is r. And as discussed, we are converting this into canonical form, right? By using x equal to py. That means the outcome is, what is the outcome in this case? Canonical form is only square terms, right? Y1 square, y2 square, y3 square. It can be plus or minus. It depends on diagonal elements. Right? So in this canonical form, we'll have positive terms, negative terms. Sometimes some diagonal element may become zero, right? So now, how many number of positive terms this canonical form is having? Positive square term is nothing but positive terms. So that number is called as index of the quadratic form. So index means number of positive terms in canonical form. Right? So another definition. Right? So here as was mentioned, the rank of the quadratic form is R, right? So therefore, if we in final canonical form, you will have R terms. That's why if you see here y r square. Right? So now suppose here, as mentioned, so total number of terms are R, right? And the number of positive terms in the canonical form, if you take, generally we denote it by S. So as discussed, it is nothing but index, right? So then total number of terms are R and S is number of positive terms, then we take R minus S, that is number of negative terms. Okay. Now the difference between number of positive terms, that is S minus R minus S, that is excessive positive terms, what we call as, that is S minus R minus S, then we'll get 2S minus R. So this 2S minus R is called as signature. Right? So two terms are important. One is index. Index is the number of positive terms. Signature is 2S minus R, where S is the number of positive terms, that is signature index, and R is rank of the matrix. Right? So these two are very important for us, right? So one is index, other one is signature, other one is rank of the matrix, next is number of variables, right? So based on this, we'll categorize quadratic forms into various types. Okay. So this is already what we discussed. So what is signature? The excess of the number of positive terms over the number of negative terms. So that is what we discussed here, right? So S minus R minus S, that is 2S minus R, right? Okay. So that is what we call as a signature of the quadratic form. Right? Okay. Now, so this is actually important thing, classification of quadratic forms. Right? So the quadratic forms are classified into the four types. One is positive definite, positive semi-definite, negative definite, negative semi-definite, and indefinite. So what is the base for this is, so when suppose a quadratic form is given and we want to classify it, whether it falls under positive definite or positive semi-definite, negative semi-definite, or indefinite kind of thing. So then what is the base? Right? How to do it? So the base for this is, first we have to convert them into canonical form. Once we convert them into canonical form, then we can have a rank of the matrix, we can have index, we can have signature, right? So based on these, so we'll categorize the given quadratic form into the mentioned four types or four classes. Or sometimes we simply say that the nature of the quadratic form or classification of the quadratic form. Right? So that is it. So then we'll see the basic definition before solving a problem. The basic definition of positive definite. So when a quadratic form can be said to be positive definite, if x transpose ax greater than or equal to 0 for all x1, x2, so on xn, right? If by chance if this x transpose ax becomes 0, it happens only when x1 equal to 0, x2 equal to 0, so on xn equal to 0. That is, various definitions are there. So other one is r equal to s equal to 1, and r equal to the rank of the quadratic form, s is signature, right? S is index, and n is number of variables, right? So if it is positive definite, then one way is from the canonical form also we can say is it a positive definite or not. Whenever it is canonical form, you will have it in the form of y1 square plus y2 square plus so on y1 square, yn square. Okay, this is one definition. Okay. Positive definite. So next is positive semi-definite. So when our whenever x transpose x greater than or equal to 0, the same condition like definite. But here the second condition is different. X transpose A equal to 0 for some value of x. There what whereas whenever this happens, then x1 equal to 0, x2 equal to 0, so on, xn equal to 0, right? Here, so x transpose x equal to 0 for some values of xi. Right? Any of the values of x1, x2, so on, xn. And third, one more other condition is r less than n and s equal to r. This is another. Or otherwise, by seeing also we can say whether it is positive semi-definite or not. Yes, how it is y1 square plus y2 square plus so on y r square. Right? So if you see the difference between the previous one, so previous one means positive definite, right? So where y1 square plus y2 square so on yn square, right? So in this case, it is up to yr square, right? Where r less than. As discussed, we know already we discussed eigenvalues, right? So when we had x transpose x, take that matrix A, take data of A minus lambda equal to 0. So then when we solve it, we'll have the eigenvalues, right? No need to go for eigenvectors, just eigenvalues enough. So if all eigenvalues are positives, then it is positive definite. So all eigenvalues are positive and they can be a zero eigenvalue. Right? Then it is something like, suppose the eigenvalues are lambda equal to 1, 2, 3. Right? 1, 2 and 3. 3 eigenvalues, suppose. So here it is having 3 eigenvalues. All the 3 eigenvalues are positive. Therefore, we say it is positive definite. Suppose one of these 1 comma 2 comma 0. So 2 are positive and 1 is 0, right? So then we call the quadratic form as positive semi-definite. Similarly, negative definite, negative semi. If all eigenvalues are negatives, then it is a negative definite. If apart from these negative values, if any one of the, at least one of the eigenvalues are zeros, that's why if you see it less than or equal to, then it is semi-negative definite. Right? Okay. So if apart from these combinations, if eigenvalues are positives, negatives and zeros, mixture of all signs, then we say that the quadratic form is indefinite. I think this way of doing we can try when it is a short answer type of question. Right? And I think down the line the same whatever the conditions we discussed earlier also mentioned for our reference sake. Okay. Right. And one more is there actually. One more idea is also there. Right? So that means to test or to find the nature of a quadratic form, 3 ways we are having. One is so converting it into canonical form, then based on the canonical form rank, index and comparison, based on that we'll go for the nature of the quadratic form. Second one is with the help of eigenvalues, right? Positive eigenvalues, positive definite, etc. So another one is, so without reducing into canonical form and there are no eigenvalues, just by taking the matrix as it is. So how we do is, now in a matrix we'll have the principal determinants. Principal determinants means, so this is a principal determinant of order 1 and this is the principal determinant of order 2, right? And this is the principal determinant of order 3. That means generally they will call as D1, D2, D3. Right? Now based on nature of these determinants we can say the quadratic nature of the quadratic form. Right? So in detail, so here this is the first determinant, A1 is only A11 and second one A2 is the second leading determinant. Third leading determinant here in this case is nothing but the determinant itself. We have to continue. If it is 5 by 5, so first one, second one, third one, fourth one, like this we have to consider. So leading determinants of the matrix, we have to find A1, A2, A3. If all these leading determinants are positives, all are positives, then it is positive determinant. Right? Out of these positives, if any one is 0, at least one is 0, that means you will have a combination zeros and positives, then it is positive definite. Right? And third case is alternatively it is positive negatives. So here if you see here, A1 less than 0, A2 greater than 0, A3 less than 0, and so on. Right? So alternatively it is negative positive kind of thing, then it is said to be negative definite. So negative semi-definite. So out of these alternate negative positive combination, if at least one is becoming 0, so then it is negative semi-definite. If other than these combination, if we find anything, then we say the quadratic form is indefinite. Right? Okay. So three ways of, so depending on our understanding, depending on the requirement, we can go for either converting into canonical form and or with the help of eigenvalues or with the help of principal determinants. Now we'll take an example. Right? So I think with this example we'll understand the concept. Now it is very important, whenever we had this topic, then this is one of the things generally they ask. So consider the quadratic form, convert it into canonical form, then find its rank and index, based on that classify it. Right? So first of all, is it a quadratic form or not? That is the basic thing. They give something, then we cannot try, right? Is it a quadratic form or not? That is the first question, right? So here if is it homogeneous or not? First question, right? So x2, 2, 2. So here also 2, here also 2, here also 2, right? So that means, so 2, every term is having the degree or power as 2, right? Combining to, not individual. So that means it is homogeneous. Right? Then next requirement is homogeneous of degree 2, right? Here every term is of degree 2, right? Therefore, this is a polynomial which is homogeneous of degree 2. So therefore, this is considered to be a quadratic form. Right? Okay. So then we'll try how we'll go for canonical form, etc., etc. So first thing what we have to do is, whenever we see a quadratic form, any expression, we have to validate, is it qualified to be a quadratic form or not, like what we discussed, right? So here validation is over. Then we have to represent this in matrix form as x transpose Ax, right? So this is a transpose or the row vector x1, x2. Here it consisting of three variables x1, x2, x3. So x transpose Ax. So how to take this A matrix as discussed. So first, if you see here, this is the diagonal, right? So diagonals represent the square terms, right? So this is x1 square, so 1, so 2x2 square, so 3x, x3 square, right? Next, this is x1, x2 term, x1, x3. We have to, now if you see here, 2x2, x3. So we have to divide this into half, right? x2, x3, x2. This is the place x2, x3, and this is the place x3, x2. Next, minus 2x3, x1. Right? Now this is x1, x3, right? And this is x3, x1. So half of here, minus 1 here, minus 1. So next 2x1, x2. So this is x1, x2, right? This is x2, x1. We have to distribute this equally. Therefore, here 1x1 and 1x1, and here also 1. Right? So like this, we have to first take the diagonal elements, which takes care of the square terms. Then remaining things we have to distribute equally, so that this, as mentioned, as discussed earlier, this is always a symmetric matrix. Right? So we have Please check it before proceeding further. By mistake, if we do anything wrong in writing this matrix, right? So whether is it a symmetric matrix or not? If it's symmetric matrix, probably whatever we have done is perfect. So next, what we have to do is, so if you remember, to convert this into canonical form, we need something B, right? So B, right? And as discussed, if B is a diagonal matrix, that is nothing but P transpose AP, right? If B is a diagonal matrix, then we can have the sum of squares terms or canonical form. Right? How to have this is, so where we need to find a congruent matrix to A, right? So that means we have to find a matrix B which is congruent to A. So what we have to do is take this transformation A equal to IAI. Right? So after taking this, what we have to do is, by applying row as well as column transformations, we have to convert this into diagonal matrix, right? So we have to convert this into diagonal matrix, and we have to be very careful here, row as well as column operations. But so whenever we go for a row operation, so we have to apply the row operation on the left hand side A matrix and the first identity matrix here. Right? And whenever we do a row operation, immediately we have to do a similar column operation on matrix A and also second identity matrix. So why we are doing this is, at the end you'll understand, because finally we require P transpose AP, right, which gives a diagonal matrix, right? Okay, so we have to convert this left hand side matrix into diagonal matrix with the help of row operations as well as column operations. Whenever we go for row operations, we perform it on the first identity matrix, similar column operation on second identity matrix. Okay, clear? So now we'll slowly do it. So first what we do is, we'll convert this into almost, I won't say it, just imagine like what we do in case of the echelon form, right? What we do when we try to convert a matrix into echelon form is better proceed with the same set of mind when we try to convert this into a diagonal matrix. So here, so we are going for operation R2 is R2 minus R1. Right? So first what we have to do is, we have to go apply this operation on this matrix and on this identity matrix. Right? After completing this, it is compulsory that we have to go for similar column transformation. Similar column transformation means R2 is nothing but C2 here, C2 is C2 minus C1. Let's see it. So this is what we get. So this is first applying the row operation, then applying similar column transformation. So we'll get this. So I think you can work out. And whenever we complete the here operation completion means row followed by column, then it is, we say that operation is completed. So then immediately you can see, so whatever the matrix we are getting here, we should get transpose of T here. That is one check when we try to solve problems. Right? So once our set of operations for now, still we have to do it. Now next what we do is, so we'll try to make this as 0 with the help of the operation R3 is R3 plus R1. Right? So first we perform this R3 is R3 plus R1 on this matrix and on this identity matrix. After that we have to go for similar column operation, that is C3 is C3 plus C1 on again the same matrix and on this matrix. Okay. This is what we get. So this is the first one is after completing row transformation, right? And by performing similar column operation, this is what we are getting. I think I have to work it out to understand it clearly. So next is, so it is over. Now still that's why what I told. Now, so imagine or try to recall what we have done in case of echelon form, right? So the first elements are over. Now we try to convert this into 0, right? Okay, so here the operation is R3 minus 2R1. 3 is R3 minus, so 2R2 actually it is. Right? So this is the operation, and similar column operation. I think we need to validate these two operations. R3 is R3 minus so it is actually R3 is R3 minus 2R2. I think there is a typo. Similarly, C3 is C3 minus 2C2. Right. So when we perform this, so the first row operation gives this and column operation gives this. When we see this, if you see here, this is what we are looking for, right? So again I repeat, after completing row followed by column, then only we have to check. Suppose if by any chance, while doing the operation, if any mistake, suppose if we got a diagonal form here, no, we should not consider, right? So after completing row and column, then we have to check. So this is the diagonal matrix, right? And if you see here, so this matrix and transpose of this, right? So that's why this is a P transpose AP, right? So B, this is the B matrix, right? So B equal to P transpose AP. Then immediately we remember, so B is congruent to A, right? That means here, if you recall the discussion, whatever we had, X transpose AX is the X transpose AX is the given transformation, right? Quadratic form, sorry. So then we are using X equal to Py. Right? X equal to Py is the transformation we are using. So after this, what is happening? It is becoming Y transpose By, right? Y transpose into By. So what is this B matrix? This is what we got. This is a diagonal matrix. What we got it, right? So that is B matrix. So this is what we have to do. Once we had this B matrix, everything is done. Now, so B is a matrix which is a diagonal matrix. P is the matrix which helps us in the transformation, which is a non-singular matrix, and that Y equal to Px is the non-singular transformation. So once this B matrix is there, very simple. So Y transpose, that is new variables y1, y2, y3, this B matrix, and then simply what we get is y1 square, y2 square minus 2y3 square. So this is the canonical. Once we have this canonical form, then based on this we can discuss its nature. So here we'll see rank and index if they asked for, right? Here A is a non-singular matrix. If we can verify it. So A is a non-singular matrix where that is not equal to 0. Even we can see it when we do the transformation, it is becoming a non-singular matrix. When that is not equal to 0, then rank of the matrix equal to 3, right? So next, index is nothing but the number of positive terms. What does it mean, number of positive terms? See, in the canonical form, we had 2 positive terms and 1 negative term, right? So the 2 positive term, that is what we are calling as index, which we are denoting it by S, right? So the S equal to, so right, 1 minute, something mistake happened. So the number of positive terms 2, right? The rank is 3. Then if you want signature, actually it is not asked. Otherwise, if you want, we can find the signature, which is 2s minus r, where s is index, that is number of positive terms 2. Rank of the matrix is 3. Therefore, 2 into 2, 4. 4 minus 3 is 1. Right? This is. So rank we have. Next, nature, if you remember or recall the process, whatever we tried, so based on that we can come out with the nature of the quadratic form. Here S less than R, that is the number of positive terms, right? That is index less than the rank of the matrix, therefore it is indefinite. Or as discussed, if you go back and see the canonical form, if you remember, if all are positives, so three are there, right? Three terms are positive, then it is positive definite. Suppose if any one of these terms is missing, that suppose y2 is not there, y1 square plus y3 square, then it is positive semi-definite. Right? Suppose if all are negatives, minus y1 square, minus y2 square, minus 2y3 square, all these three terms are negative, then it is negative definite. Suppose any one of these terms are missing, then negative semi-definite. Right? So in this case, what we observed, it is a combination of positive square terms as well as negatives, right? That means it is indefinite. Right? So it is indefinite form. Okay. So this is how we can find the nature of a quadratic form. Okay. Now, so this same, like I think we'll see this one example. Classify 2xy plus 2yz plus 2zx without reducing it to canonical form. Right? So we don't want any x equal to py kind of stuff. So without doing all those things, so find the nature of the quadratic form. So first thing is it a quadratic form or not? So this is 2, 2, 2, right? That means homogeneous polynomial of degree 2. Therefore, it is a quadratic form. Right? So without reduction means for which we will take the leading determinants, right, as discussed. Right? So first, let us write this in matrix form. So when we write this in the matrix form, what is A matrix here? So what is A here? So there are no square terms, right? Therefore, so no x square term, no y square term, no z square term, right? 2xy, so half of 1xy, 1xy. 2yz, so half here, half here. And 2zx, so xz here, zx here, right? So this is the matrix A from the. Now we can verify it. This is a symmetric matrix. Okay. So once we had the symmetric matrix, in this method, what we'll take the principal determinants. Principal determinant is so first determinant is this order 1, D1, what we call as. So that is A1, which is 0, and A2, that is determinant of order 2. So this is second determinant, D2 this is. Right? So 0, 1, 1, 0, if we expand this, it is minus 1. And A3 is the third principal determinant is the complete matrix here, the complete determinant here. So which is 2. Right? So now based on this we can categorize, right? So one is, if you just to as a recap, so if all are positive, then positive definite. All these A's are positive definite. If any one of these A's are negative zeros, then it is positive semi-definite. Right? Alternatively, changing, that is negative, positive, negative, that is A1 is negative, A2 is positive, A3 is negative, and so on like this, then it is negative definite. In the same here, if any principal determinant is becoming 0, then it becomes semi-definite. If it fails to fit into any of these cases, then we call it as indefinite. Right? So this is how we can discuss the nature of a quadratic form. So how the question appears in general in any of the examinations. So they give a polynomial like this, expression like this. So one way is reduce the following quadratic form into canonical form. That is one way. The other way is discuss the nature of the quadratic form. That is another way. Third, another way is diagonalize the quadratic form and hence discuss its nature. That is another way. Another way is convert this given expression is polynomial or quadratic form into sum of squares form. The term also we need to remember, instead of, because we are familiar with respect to canonical or normal form, they can mention it as sum of squares form. Sum of squares. Right? Sum of squares, SQARES. Okay, so this is another right. So here actually just I took only the problem. You can try the solution. Right? Okay, that is what we discussed. To summarize, what the session today, what we discussed is basically what we have done is we discussed the quadratic form. So what is a quadratic form? To summarize, quadratic form is nothing but a polynomial which is homogeneous of degree 2 is a quadratic form. So immediately what we tried is we tried the matrix representation of the quadratic form, which is x transpose Ax. Right? X transpose Ax. So even for sometimes for short answer, this is one of the prospective bit, like convert the given quadratic form into matrix form. Right? So where A is a symmetric matrix. This is. So next, after this, we discussed the transformation of this X transpose Ax into canonical form, that is Y transpose By. Y transpose. So this is actually the main conclusion or take home kind of stuff from today's discussion. So converting this X transpose Ax into Y transpose By is a transpose. Y transpose By, where this B is a diagonal matrix. So this is called as canonical form, normal form, sum of squares form, etc. etc. So based on this Y transpose By, we discussed its nature. Nature means here positive definite, positive semi-definite, negative definite, negative semi-definite, indefinite. Right? So converting quadratic form into canonical form, then with the help of rank and index, we can arrive at the nature, or by seeing the canonical form, right? So number of positive terms, by seeing the canonical form also, so we can say the nature. So one way is, so with the help of rank, index, etc. Second one is with the help of the representation, just how many positive terms are there, how many negative terms are there. Based on that also, we can comment on the nature of the or classification of the quadratic form. Third, one more method is, so without doing these transformations, what we can do is take the matrix A, so find eigenvalues of this matrix depending on the nature of eigenvalues. If all eigenvalues are positive definite, out of these positive, at least if one eigenvalue is 0, then positive semi-definite. All eigenvalues are negative definite. Out of these negatives, if any one is 0, negative semi-definite. If eigenvalues are combination of positives and as well as negatives, indefinite. That is another approach. Right? Eigenvalues, eigenvectors. So another approach where we can discuss the nature of quadratic form is with the help of determinants, right? With the help of determinants d1, d2. The determinant here is not irregular. So determinant discussion what we leading determinants like d1, d2, d3. So based on determinants also we can classify the given quadratic form. Okay. So this is what we plan to discuss in today's session. So the coming session will take some theorems or properties related to quadratic forms. Right? Thank you.